We made it to chapter 4. This is where we are finally going to get to see what mass flowing in and out does to our systems. This chapter is going to be called Control Volume Analysis Using Energy, and we are going to start off by talking about conservation of mass. We are going to consider a control volume. Remember control volume, we talked about that in I think the first lecture. And that's where we said a control volume was going to have mass flowing in and out. Okay, so we're going to consider a control volume with mass flowing in at the inlet and flowing out at the exit. So let's draw an example here. So let's have something that looks like this. You guys know by now I'm not a very good artist here. We've got mass coming in right here. That's the inlet. This is the exit. We've got mass flowing out. This will be our control volume. And what you typically see, let me switch colors here, is you'll see a dashed line here, and that's going to represent your control volume. All right, so think of this as being your boundary. You got flow going in, going out. Typically this is going to be perpendicular to the flow. So these are the types of problems we're going to be talking about. This is one inlet, one exit. We will expand on that when we have multiple inlet, multiple exit problems. Let's go over conservation of mass first. And you probably saw this if you've taken a physics class. Conservation of mass is going to state that the net change of mass within the control volume, and I'm just going to write that as CV, during a time delta t has to equal the total mass entering the control volume during that time dt minus the total mass leaving the CV during delta t. That is what conservation of mass states. And that'll give you the net change. So we have to look at what's entering, what's leaving. Now it's important to note that these are during the same time periods. Okay, so you can't compare different time periods. That wouldn't make any sense. Now if we put this in a more mathematical form, we could write the change, or delta, of MCV. This is stating the change in the mass of the control volume. That's got to equal the mass coming in minus the mass going out. Pretty simple equation there. We also have a time rate form of this. So by time rate form, think derivative. We're going to write dmCV over dt. That's going to equal mn dot. Remember that dot just means time rate. And then we're going to subtract m out dot. Let's label what these things are. This term here is going to be the time rate of change of the mass within the control volume. Units for this will be kilogram per second in the metric system, or pound mass per second in the English system. Now on the right side we've got this mn dot. This is going to be the rate of mass flow into the control volume. The units here, you can probably guess, since this is kilogram per second, this one also has to be kilogram per second or pound per second. And m out dot, that's going to be the rate of mass flow out of the CV. Units here, kilogram per second and pound per second. So essentially what this is telling you, it's how many kilograms per second you've got flowing out of your control volume. And this one would be how many kilograms per second are flowing in to your control volume. And this one will be the change. Now this is for one inlet, one outlet. We typically are going to have more than one inlet, one outlet problems. So for several inlets and exits, let's expand that equation. It's going to be pretty similar. We'll have, let's move this up here so you can actually see it. We'll have dmcv over dt, so the time rate of change of the mass in the control volume. That's now going to equal the summation over all of the inlets of mn dot minus the summation for all of the outlets of m out dot. So essentially each inlet you have, you're going to find the mass flow and you'll sum them all together, and then you'll subtract the mass flows for all of the outlets. So pretty simple calculation, really. And let's call this equation 1. Next, we're going to talk about one-dimensional flow. This is the kind of flow we're going to have in this course. We're not going to get too crazy with the flows that we're going to look at. You guys have enough to learn alone with one-dimensional flow. For one-dimensional flow, flow is going to be normal to the boundary where mass enters and exits. And that's what we saw in that little drawing I did. Remember I said it'd be perpendicular. So we're always going to have it be perpendicular. That's the simplest way to do it. Now, we're also going to say that velocity and density are going to be uniform with position over the inlet and exit areas. So that means if we have, think of a circular area, we're going to assume velocity and density are the same anywhere in that circular area. Right, so we're not going to worry about how the position in the area might change those parameters. We'll just assume they're all the same. So that'll be a good thing. Now let's get another equation. M dot, we need to know how to find this. This value for mass flow is going to equal rho times a capital V. And let's box this because you will definitely need this. So let's put a star by it. And let's put down what each of these terms are. So rho, you should know that one. That's going to be density. A is going to be your area. And let's draw a picture to go over this. So let's say we have a circular opening here and it's flowing into something that looks like this. All right, so we got mass entering. The area is going to be this cross-sectional area right here where the flow is entering into the system. Okay, and then finally we've got V. Now, what do we think that V is? We've had two other V's already, right? We've had volume, we had specific volume. So what do you think that one might be? Right, it's going to be velocity. I'm sure you were all thinking that. So it's going to be velocity. And now if we look at our units, because you know I like to look at units, we're going to have kilogram per cubic meter for density. Area is going to be meters squared. Velocity is meters per second. So notice all the meters cancel. You end up with kilogram per second, which is what we said the units should be. Now this equation has density. As we have seen before, we don't use density all of the time. A lot of the time we use specific volume. So we can come down here and rewrite this equation. And we can say m dot is equal to AV over little v. Now you see in this equation, this is why it is important to distinguish between your v's, because otherwise you're going to have to make sure you really remember which is which. This V here is specific volume. Remember, that's just 1 over rho. So we're just rewriting that equation in terms of specific volume. Now in the top, we've got this product A times V. A times V has a term for it. Let's go over what that's called. That's going to be called the volumetric flow rate. And let's think about what the units would be here, and then you'll understand why it's called that. So if we've got A, that's square meter. If we've got V, which is velocity, we've got meters per second. Now if you put all this together, you get cubic meters per second. Cubic meters is units of volume. So we say we have a volumetric flow rate. So our units will have cubic meters per second, or if you're in the English system, you got cubic feet per second. So this just tells you how much volume you have flowing per second in your system. Now we've got a couple of other things to talk about before we get finished with this. To round this section out, let's go back to our equation 1. In case you've forgotten, this was the equation 1, several inlets and exits. So we're going to be looking at that equation. Let's put from 1. If we rewrite that equation in terms of this, we can say dmCv dt equals the summation over all the inlets of AV over V minus the summation over all the outlets of AV over V. Alright, so now we've got that. And last thing we want to talk about is steady state. We mentioned this before in one of the first lectures, and I said that this would be really important. This is going to be another keyword, remember? And do you remember what we said was special about steady state? It is the fact that properties do not change with time. And that is important because if you look in our expressions, let's just look at this one for example. We've got dmCv dt. We're trying to take the derivative of the mass of the control volume with respect to time. So if we have a steady state system, that means our properties don't change with time. So that, by definition, means that this term is going to equal what? That's right, it's going to be 0. What a simplification. That is something we want. Now, if we have that, if we go back to that equation 1, that is going to tell us that the sum over the inlets of the mass flow rates coming in, they have to equal, or that has to equal the sum over the outlets of the mass flow rates going out. This is only for steady state. So some people like to try to use this at all times. It's only for steady state though. But that gives us a nice simplification because we no longer have to worry about this derivative term. Anytime we can get rid of those derivative terms, we want to do that. That's the end of the notes here, so we will hit the next example in the next video. I will see you guys there. You'll have a great afternoon or morning, whatever time of day it is. See you soon.